All right, in this section, we're going to examine some properties that allow us to simplify exponential expressions. So first, just a reminder what it means if we're raising a to an exponent, a positive integer exponent. It's just that exponent indicates how many factors of a that we have, right? How many times we're multiplying a by itself. We begin with this product rule, or how we simplify a product of exponential expressions. Now, if the bases are the same, this is really important, it's a to the n times a to the m. So if those bases are the same, then we can add the exponents together. And that's basically because, here we have n factors of a, and we're multiplying it by m factors of a. So altogether, we have n plus m factors of a. And here's an example of where we can use it. If I have 7 to the 6th power multiplied by 7 to the 13th power, this is simply 7 to the 6th plus 13th power, or 7 to the 19th power. And that'd be the simplified exponential expression. Similarly, if we're dividing expressions that have the same base, again, they must have the same base, a to the n divided by a to the m is a to the n minus m. We can just subtract those exponents. So over here, x to the 12 divided by x to the 8th, this is x to the 12 minus 8, or x to the 4th. If we're raising an exponential expression to a power, so I have a to the n and I'm raising that whole thing to the nth power, then we can multiply the exponents together, a to the n times m. Over here with our example, y cubed raised to the 8th power, that's y to the 3 times 8, or y to the 24th power. These next two properties tell us that how we can simplify an expression that involves a product or a quotient that we're raising to a power. It basically says that we can distribute an exponent over multiplication and division. So this first one, we can distribute an exponent over multiplication. A times b, all raised to the nth power, is a to the n times b to the n. So for example, 3x, all to the 4th power. This is 3 to the 4th power times x to the 4th power, and then we could evaluate 3 to the 4th. I think that's 81. So we get 81 x to the 4th. We can distribute an exponent over division. So if I have a fraction, a over b raised to the n, that's the same as taking a to the n and dividing it by b to the n. Here we have 2x over y, all to the 3rd power. So we're going to use a couple of properties. First, this property that tells us we can distribute over division. So we have 2x all to the 3rd over y to the 3rd. And now up top, we have a product to the 3rd power. So we're going to go back and use that previous property. 2 cubed x cubed over y cubed. And we can evaluate 2 cubed. That gives us 8. So we have 8x cubed over y cubed for our simplified expression. You might just notice here, before we go on to the next one, that, looking at what we have started with, and then this part here, if my expression that we're raising to a power involves multiplication and division, you just take each of the individual factors that appears in the top and the bottom, right? Each of those factors is raised to the 3rd power there. The zero exponent. Anything raised to the 0 power, any non-zero base raised to the 0 power is equal to 1. This is sometimes a little bit unexpected, or people think that maybe if I raise something to the 0 power we should get 0. But I'm going to show you why. I'm going to do a little mini example here in this middle box. If I take 2 cubed and divide it by 2 cubed, well, on the one hand, I'm taking an expression, dividing it by itself, so that's got to be equal to 1. However, I could also take this fraction and use the property that tells me that when I'm dividing expressions that have the same base, I can subtract the exponents. So this is 2 to the 3 minus 3, or 2 to the 0, and now just compare, right? The expressions on the very left and the very right have to be equal, and you could come up with with an example for any base you want to show that that base raised to the 0th power is equal to 1. We just want to make sure we're careful about observing what the exponent is on, and that's true regardless of the expression. What it's we want to make sure we're aware of what base an exponent is being applied to, right? Regardless of what property we might be using. But that's really shows up pretty well in this example. If I've got two examples here that look quite similar. Up here, up top, we have 1.2 pi in parentheses all to the 0, so that whole base is 1.2 pi being raised to the 0 power, and this property tells me that's equal to 1. At this next example, 1.2 pi to the 0, here that exponent, 0 exponent, is only on pi, right? There's no parentheses, so it's just on pi. So this is 1.2 times 1, or 1.2. And then this last property says, just defines the negative exponent for us. So if I'm raising a to the negative n power, that is defined to be 1 divided by a to the n. For example, 8 to the negative 2 is 1 over 8 squared. Note that a negative exponent doesn't make anything negative. It makes it small, right? It puts it in the denominator. And if we want, we could evaluate this, simplify it. 8 squared is 64. So 8 to the negative 2 isn't a negative value. It's just this small fraction. And you can. I'm going to do a little extra extension of this. A to the n is defined to be 1 over a to the n. 1 over a to the negative n is the same as a to the positive n. When you see a negative exponent, you can kind of think of it as just, switch its position from the bottom to the top or the top to the bottom in order to make that exponent positive. We have to be really careful. We learned some properties just on the last page that allow us to simplify things. They're really convenient. Two of them had to do with when we can distribute an exponent. We can distribute an exponent over multiplication and division. We cannot distribute an exponent over addition or subtraction. So if I'm adding or subtracting, I want to just slow myself down and make sure I'm not doing anything I'm not allowed to do. And just to illustrate and convince us that we're not allowed to distribute an exponent over addition, I'm going to look at this numerical example. On the left side, we have 3 plus 4 in parentheses squared. Well, using the order of operations, I know I've got to do the addition in the parentheses first, so that's 7 squared, or 49. On the right side, 3 squared plus 4 squared is 9 plus 16, or 25. And I think we will all agree that 49 is not equal to 25. So that means that these expressions here are not equal. We cannot distribute an exponent over addition. So we're going to do some examples now where we are simplifying exponential expressions. I'm going to apply these properties that we've been learning. First, here we have ax squared times ax in parentheses cubed. So I'm going to, the first thing I'm going to do is just deal with this part. So I have ax squared times, and that highlighted part will be a cubed x cubed, because I can distribute an exponent over a product. Now, we're multiplying here. Everything is being multiplied, right? There's no addition or subtraction. I can multiply in any order that I want. So I'm going to regroup these factors. A times a cubed, and of course that first a is a to the first, and then times x squared x cubed. And if I take a look at that product, I can add those exponents and get a to the fourth, and for this product I can add those exponents and get a to the fifth, x to the fifth. I took the time to kind of rearrange the product there, right? So group the A's together and the X's together. A lot of the time, and you might find yourself doing this as well after, some practice, people will often skip this step and go straight from here to here and just sort of mentally group those together to get that final result. All right, let's do another one. We have up top a product raised to a power, so I'm going to distribute that square across that product. So we have r squared times y cubed squared. On the bottom, we have r times, now y squared to the fourth, we have that property that says when I'm raising a power to a power, I can multiply those together. So this will be y to the eighth. Up here, I can also raise a power to a power and multiply these exponents here together. So we have r squared y to the sixth over r y to the eighth. And now we can just take one base at a time. We're doing some division, so let's say I'll take a look at these first. I've got r squared over r to the first, and that's r to the first if I subtract the exponents. Y to the 6th over y to the 8th is, let's see, subtracting those exponents gives me y to the negative 2. And so simplifying this, usually the instructions will say, as they do here, use positive exponents in the result. So I'm going to write this as r over y squared. All right, let's try another one. We have a fraction raised to a power, so I'm going to start by distributing that exponent over the fraction. So I've got a cubed t raised to the negative 2 up top, divided by, on the bottom, b squared x to the negative 2. Now we want to deal with these negative exponents, and I think I'm going to do that first. I'm going to look at this and just sort of swap these the expressions in the top and the bottom, because a cubed t to the negative 2 up top is the same as a cubed t to the positive 2 on the bottom, and b squared x to the negative 2 on the bottom is the same as b squared x to the positive 2 up top. Now I'm going to distribute these exponents over the product. B squared squared times x squared over a cubed squared times t cubed. And finally, raising the power to a power, I'm going to multiply exponents. So I've got b to the fourth x squared over a to the sixth t squared. Okay, so now we're going to work with some powers of 10 and talk a bit about scientific notation. After we learn this stuff about simplifying exponential expressions, it's sort of a good time to dive into scientific notation. So if I'm raising 10 to a positive integer exponent, like 10 to the n just corresponds to the number 1 with n zeros after it. 10 to the negative n, it corresponds to 0 point, and then let's see, so obviously it's less than 1, right? 10 to the negative n is 1 over 10 to the nth power, so it's a small number, and you just put 1 n places over from the decimal point. If you want to still think of it as counting zeros, you can, as long as you count the 0 to the left of the decimal point. There's still n zeros there. So 10 to the 9th is 1, followed by 9 zeros. And 10 to the negative 6, I've got a total of 6 zeros if I count the 0 to the left. So 1, 2, 3, 4, 5, 6, 1. So there's sort of a simple way to think about it. This is the same as 1 over 10 to the 6, 1 over a million, and you'll notice that we have the 1 in the 1/1,000,000th spot there. Okay, so numbers in scientific notation, if it's written in this form, so I've got a times 10 to the n, where n is an integer, could be positive or negative, and a is a number between 1 and 10, so it's at least as big as 1 and less than 10. We use scientific notation usually to write numbers in a convenient way, numbers that are either really, really large or very, very small. And for very large numbers, the exponent on 10 here is a positive, and for very, very small numbers, that exponent on 10 is a negative. So if I want to convert from decimal notation to scientific notation, the first thing we do is figure out what is that number a that we need to use. Like, what is this value right here? And then we'll figure out what is my exponent on 10. And it's really kind of a simple process. Like, I look at a number, and actually maybe we'll just start by looking at this example here. So I've got the number 149,600,000. And what I want to do first is say, okay, in this number, where would I need to place the decimal point so that I ended up with a number between 1 and 10? And that is, of course, right here. That's the only place I could put the decimal point and end up with a number between 1 and 10. So I'm going to start with that. There's my value for A, 1.496. And then the question is, what's the power on 10? So to figure out what the power on 10 is, I say, okay, well, where did the decimal point start out? And this is a whole number, so really it started out there. And then I just count how many spaces I needed to move that decimal point. 1, 2, 3, 4, 5, 6, 7, 8. I had to move it 8 spaces. And now, so this exponent is either 8 or negative 8. And I know that it's positive 8 because this is a really big number. Right? So really big numbers, those are the ones that have positive exponents on 10. So there's that value in scientific notation. Here's another example. They give us a very small number, 0.00011. So again, I'm just going to think about where do I have to put the decimal point to get a number that's between 1 and 10. And the only place I could choose is right there between those two ones. 1.1 times 10 to some power, right? That's the next thing I need to do is just figure that out. So I had to move the decimal point 1, 2, 3, 4 spaces to the right. That's going to be a negative exponent. Some people remember whether it's negative or positive exponent based on whether we move the decimal point to the left or to the right. I usually just think about, was this a really big number or a really small number? This was a really small number, so I know it's going to need a negative exponent on the 10. Going the other way, if I'm looking at a number that is already in scientific notation, I could think of this number as a set of instructions almost, right? So I've got 2.6 times 10 to the 7th. The times 10 to the 7th is kind of telling me, okay, move the decimal point 7 spaces. And it's a positive 7 power, so I know this is a really big number, and that means I'm going to have to move the decimal point to the right. So let's see. 1, 2, 3, 4, 5, 6, 7. So, and then in all these empty spaces, I gotta put zeros. So 2.6 times 10 to the 7th is 26 million. Next we have the number 7 times 10 to the negative 6. This is a really small number, right? It's a negative exponent on 10. It's a tiny number. That means I'm going to take the decimal point, which since 7's a whole number, that means it's right here, and I'm going to move it 6 spaces to the left. Oh, whoops. 1, 2, 3, 4, 5, 6. I gotta put zeros in these empty spaces. So 7 times 10 to the negative 6 is the 0.000007. So scientific notation is convenient, often preferred when we're working with numbers that are either very, very large or very, very small, because otherwise you can kind of get lost in a sea of digits and a whole bunch of zeros. And it makes it easy. It kind of just says, okay, here's these first few non-zero digits, and then this is how big or small the number is. That size of the number indicated by the power on 10. It can also make computations simple. Multiplication, division, and raising to powers is a lot simpler if the numbers are in scientific notation. So, and we can use what we know about working with expressions with exponents to help simplify the process. So here in this example, we want to multiply 3.4 times 10 to the 9th by 2 times 10 to the negative 5th. So the first thing we'll notice is that this is all multiplication. And I can rewrite multiplication in any order I want, so I'm going to write it like this: 3.4 times 2 times 10 to the 9th times 10 to the negative 5th power. And then I can group the products the way I want. So I could multiply those two first. 3.4 times 2 is 6.8. And now this part on the end, 10 to the 9th times 10 to the negative 5th. That's, I'm multiplying exponential expressions with the same base. So I can add those exponents. 9 plus negative 5 is positive 4. And I didn't need a calculator to do that. Sometimes I might still need to use a calculator to do some of this arithmetic, but this was really quite simple, and it almost became more of a mental arithmetic problem after I kind of was able to rearrange the order of the factors. And that's a lot easier to do this in scientific notation than if I had written these out in decimal notation. Division is also pretty simple, and the way I'm going to do it is just kind of split up this fraction over over this product, right? So this is the same as 8.2 over 3.2 times 10 to the negative 7 over 10 to the negative 2. I'm basically just using what we know about how you multiply fractions, but then using it backwards, right? So usually we're already familiar with, if I start with a product like this, that I can, just multiply the two tops and put them on top, and multiply the two numbers on the bottom and put them on the bottom. So that fact works in both directions, and I'm just taking advantage of that now. Now here, I'm actually going to use a calculator to do this division, because I can't do that first one in my head. So 8.2 divided by 3.2 is 2.5625. And this, I'm going to use our property that says if I'm dividing expressions with the same base, I can subtract the exponent. 7 minus a negative 2 is 7 plus 2. Oh, that's a negative 7 minus a negative 2 is negative 7 plus 2, or negative 5. So this is 10 to the negative 5th power. And there's the result. Doing this kind of arithmetic is usually so much easier with scientific notation, to the point where even if I started with numbers in decimal form, I might just convert them to scientific notation first. So let's say I want to find this product. I'm gonna convert each of these numbers to scientific notation first. So this first number, I'm gonna have to put the decimal point between the 6 and the 4. And in order to do that, I have to move this decimal point 1, 2, 3, 4 spaces. So I have 6.4 times 10 to the negative 4, because that's a small number. And I'm multiplying this by, let's see, here I'm going to have to put this decimal point in that spot between the 9 and the 4. And in order to do that, I have to move the decimal point 3, 6, 9 spaces to the left. So 9.4 times 10 to the 9th. Again, I can rearrange the product. So 6.4 times 9.4 times 10 to the negative 4 times 10 to the 9th. I'm going to do this product first. 6.4 times 9.4. That's 60.16. And then using the rules of exponents here, adding those exponents, negative 4 plus 9 is positive 5, so 10 to the positive 5th. Now it feels like we've reached an ending point and we're almost done, but we're not quite done. This problem says express the result in scientific notation. This number is not in scientific notation. Take a minute right now, maybe pause the video, see if you can examine and find out why it's not in scientific notation. This number is not in scientific notation because this number in the beginning isn't between 1 and 10. It's too big. So in order to make this number between 1 and 10, I want to put the decimal point here. I'd have to move it back one spot. In order to do that, moving the decimal point to the left one spot, moving it back one spot, is like dividing by 10. So I'm going to make up for that. I'm going to compensate for that by adding 1 to this exponent. So we get 6.016 times 10 to the 6th power. There it is in scientific notation.